Hello everybody, Jake here, and today we're going to be talking about something that you will probably encounter in pretty much any technical field at some point. They are the permutation and combination formulas. Now, the permutation formula, let's just say you have 7 objects, and you want to choose 4 of them where the order matters. How many ways are there to do that? Well, there are 7p4 ways to do that. And similarly, let's say you have 13 objects and you want to know how many ways are there to choose 8 where the order doesn't matter. So this is combinations instead of permutations. Basically, combination, the order doesn't matter. Permutation, the order does matter. But you're choosing this many objects out of a pool of this many, and you're counting how many different ways there are to do so. Now, these have formulas, and they're well established and they're well defined, but it might not be clear where exactly those formulas come from. So what I'm going to do is I'm going to give you some very basic combinatorics examples, and we're going to derive from scratch where exactly these come from. Let's say I have these 7 cards out in front of me, and I want to know how many different ways are there to arrange these 7 cards. In other words, how many different orders can these cards go in? Now, I know some of you have probably seen this before, but I'm just trying to make sure everyone's on the same page, so I'm going to explain it from scratch. Now, you could try to systematically switch up all the cards and list them in order. Just make a whole list of all the possible different orders that they go in, and do it in such a way where you don't repeat any, but this is going to take forever with 7 cards. And furthermore, you're probably going to make a mistake somewhere along the line. So, is there a smarter way to do this? And yes, there absolutely is. If we just set aside all 7 of the cards, notice how there are 7 different possible choices of a first card. So let's just say we pick the 4 first. Now that we've picked the 4, there are 6 possible different choices of the second card. And if you noticed, even if we pick the 5 instead of the 4, there will still always be 6 different choices of the second card after we pick the first one. So, in other words, for each of the 7 cards, there are 6 choices for the second card, so we actually multiply by 6. And let's just say we pick the 7 next. Now, there are 5 cards left. No matter what the first 2 cards we chose were, there will always be 5 different cards to choose third. So, we actually multiply by 5. And we can keep doing this. The pattern will simply continue. So there are 4 choices of the 4th card. There are 3 choices of the 5th card. 2 of the 6th card. And once you've picked 6 cards, there's only going to be 1 left. So for each of the starting selections of 6 cards, there's only 1 remaining way to choose the last card. Now, if this is your first time seeing anything like this, you might be a bit skeptical, so I'm going to explain it in another way that's hopefully maybe more convincing to you. So let's set aside all but 2 of the cards. Now, notice, we can easily see that there are 2 different ways to order the cards. So we're just going to write down 2. Now, let's add a 3rd card to the mix. What we can do is we can actually take this 3rd card and sort of separate it and see that for, the 3rd card being in the spot over here, there are 2 different ways to arrange the remaining cards. And if we have the 4 out here, we could switch these 2 cards, and there are 2 different ways to arrange them. And there are 3 different possible choices at this point of the card we set aside. So there are 3 choices of this card times the 2 ways to arrange the remaining cards. And if we add a fourth card, we could see that this will continue going on. Let's set aside this fourth one for now. And notice that there are 3 cards remaining. Well, as we just showed, there are 3 times 2 ways to arrange these 3 cards. So that goes for this selection of the first card. If we set aside the 6 instead, there will also be 6 different possible arrangements. So for each of the choices of the card to set aside, of which there are 4, there are 3 times 2 ways to arrange the remaining ones. And this will continue. So there are 5 different choices now of a card to set aside. And there are 4 times 3 times 2 ways to arrange the remaining ones, whatever your choice may be. And we're going to, count all the way up naturally to 7. So you can count either down or up, but the important part, and by the way, we also can say that, if we have only one card, there's only one way to arrange it. This kind of goes without saying. So, point is, if you have n objects, there are n times n minus 1 times n minus 2, and so on, times 1 ways to arrange those n objects. And we call this n factorial. So this number right here, this will be 7 factorial. The exclamation point, you'll be seeing it a lot in the rest of this video. So this is very important to note. Now we're going to move on to a slightly different problem. Let's say we have these 7 cards. And what I want to know is, how many different ways can I arrange these 7 cards where only the value matters, not the suit? In other words, if I were to switch this ace of clubs for this ace of hearts, this is now the same order. So how many different arrangements are there now? Now, you might say, oh man, this really isn't as simple as just 7 factorial anymore. Do I now have to regress to just listing them out systematically like I was going to do before and trying to make sure that I list all of them? No. There's a much better way to do this. And in order to see what that way is, what we're going to do is we're going to take this order of cards and just isolate the aces. So we have this order of cards, but anytime I rearrange where the aces are, it still counts as the same order. That's kind of the problem definition, but when we isolate it like this, we can see something. How many different ways are there to arrange these 3 aces within this order of cards? Well, there are 3 aces, so naturally, now that you're experts, it's 3 factorial. So there are 3 factorial different ways to arrange these 3 aces that are redundant. So only one of them will actually count. Now, let's do a little change here. Let's just change this ace for this 2 and this ace for this 5. And then we're going to isolate the aces again. Now for this order of cards, once again, only one of the 3 factorial possible different orders where the aces are somewhere, in these slots actually count. In other words, let me put it like this. If I have a list of all the different orders and so on, and I mark off all the different orderings that are redundant with this one, so let's just mark them, what we're going to find is that there are 3 factorial different orders and one of them counts. And the same goes for this order of cards. There are 3 factorial different orders where everything is the same except the aces are in different spots. But only one of those 3 factorial will count. So notice that there are 7 cards. Let's not forget there are 7 factorial different ways of arranging them. But for each of the arrangements, only one of the 3 factorial actually counts. Because the other 3 factorial minus one of them are redundant, they're just the same thing except with the aces in different spots, which we don't want to count again. So, in other words, our final answer should be 7 factorial over 3 factorial, which will end up being 7 times 6 times 5 times 4. And that's how many ways there are to arrange these 7 cards where only the value matters, not the suit. Now we're going to change this up a little again. So now let's say this is my selection of 7 cards. And we're going to ask the same question again. How many ways are there to arrange these 7 cards where only the value matters, not the suit? The difference between this and the last one is I took out the 5 and replaced it with the second 2. So now there are 2 2s. So this might be a little tricky if you don't already know the answer. So like what we could do is we could isolate the aces, and we see that only one of the 3 factorial different ways to arrange the cards where the aces are in the spot actually count. But then we also have to consider these 2s, and like, do I add? Do I multiply? What goes on here? Well, let's do this. Let's take all 5 of the cards where there might be redundancies, and we're going to isolate them. And once they're like this, we're also going to isolate just the aces now. Now we know that there are 3 factorial different ways to arrange just these aces. So if we were to list out all the different ways to arrange these 5 cards that are in these particular slots, only one of the 3 factorial counts. But then what we do is we note that we can just switch the 2s, and this is also redundant. So of that 1 over 3 factorial fraction of the arrangements that actually are different from each other, only one of 2 factorial actually count, because the other one is just the same thing with the 2s switched. Now I'm going to go over that one more time because I just said a lot in one sentence and it might have been confusing. So we have these aces isolated, and there are 3 factorial different ways to arrange them. And, if we repermute these, we'll see that only one of these 3 factorial should actually count. And let's just choose one of the 3 factorial ways to arrange these aces and lock it in place. We can see that only one of 2 factorial of those should actually count in our overall count of the number of orders that we could place these cards in. All right, so all we do is we multiply the fractions that we would have found if we did them individually. And in fact, we could actually, in theory, isolate the 3 and the 4 as well. But 1 divided by 1 factorial is just 1, and multiplying by 1 doesn't really do much, so we don't really talk about it so much. However, they do technically count as their own categories. So if we have 4 categories here, aces, 2s, 3s, and 4s, then all we have to do is we take this 7 factorial, we divide out the number of ways to arrange all the items in each category. So it would be divided by 3 factorial times 2 factorial times 1 factorial times 1 factorial. But we really don't have to write down this 1 factorial part because it's kind of, a little bit redundant. So that is our answer, 7 factorial divided by the product of 3 factorial and 2 factorial. Not sure exactly what number that is, but it doesn't really matter for our purposes. This is our answer as far as I'm concerned. Now I know what you're thinking, Jake, this is all well and good, but what on earth does all this have to do with the original question? What is the relevance to the combination and permutation formulas? Well, I'm about to demonstrate. So imagine we have these 10 objects to select from, and we want to know how many different ways can we choose 4 of these objects where the order actually matters. Now, there is a pretty intuitive way to think about this, and it's very similar to what we did when we derived that there are n factorial ways to arrange n objects. Our first object we select, there are 10 possible different objects. Now, for each of these initial selections, there are 9 remaining possibilities of the second object we select, and 8 possibilities for the third, and 7 for the fourth. So this is a nice, simple, succinct, and very intuitive way to, get an answer to this problem. However, what we're going to do instead is do it in a bit of a different way. So what we're going to do is we're going to ignore the first 4 objects, and we're going to box around these 6. Now, imagine these 6 boxes are slots where you can insert the object into, where they don't get selected. So this order of objects corresponds to triangle, square, circle, star as our selection, and all of this as our non-selection. Now, you know already that there are, of course, 10 factorial different ways to arrange these objects in order. And each of these orderings corresponds to a selection, but some of them are redundant. For example, if I were to switch this squiggly line with this backslash, then our selection of 4 still remains the same. Now, if you recall when I was mentioning object categories earlier, for example, the aces were a category and the 2s were a different category, what we could do is we can actually treat these 6 objects as a category. So there are actually 6 factorial different ways to arrange these 6 objects. So if we were to list out all of the 10 factorial ways to order these objects and then mark off the ones that were equivalent to this selection of 4, triangle, square, circle, star, then we would find that there are 6 factorial similar ones, and we only want to count one of them. So only one of 6 factorial counts. In other words, we just divide out 6 factorial. And this is indeed the correct answer, except what I want to do is I'm going to rewrite this as 10 minus 4 factorial. And you'll see why in a second. Now, in case you're kind of wondering, if I were to write this out manually, we would get 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And in the denominator here, we would get 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. This would all cancel out, and we're left with 10 times 9 times 8 times 7, which, hey, that's what we got earlier. All right. It aligns with what we would expect. And in fact, the fact that you can do this in a much more intuitive and easy to think about way like this is why you don't see the permutation formula as much as the combination formula, but this is still useful to know. So if we have n objects, we want to know how many different ways there are to permute r of them out of this pool, then all we have to do is take n factorial and divide n minus r factorial. So pretty simple, right? Hopefully that makes sense. If it does, then this next part is gonna be pretty simple as well. There's just one further complication. Now, let's say we have mostly the same problem, except with one difference. The order in which we pick the 4 out of the 10 doesn't matter. In other words, all we want to know is how many ways are there to choose 4 objects out of a pool of 10. Now, as you can see right away if you're just thinking about it, this problem comes up a lot more frequently in real life. You will encounter this, many times if you're working on statistics and combinatorics, but even if not, this is something you might want to know from time to time. And it's also a lot harder to count than just the permutation formula. Like, there's no easy way to do it where you just think of how many ways are there to choose the first object, then the second object, and so on, because it's so easy for there to be redundancies. It's not true that for each of the 10 objects you start out selecting, there are 9 possible other objects to select that would actually count. So we're going to do something fairly interesting instead. What we're going to do is we're going to actually add more boxes and finally make this look a bit more complete. So now all 10 of our objects are in slots instead of just the 6. And, if you're thinking about this as I speak, then you probably know exactly what's going to happen next. Notice how if we were to switch, for example, the square and the circle, this is the same selection of 4 objects out of the pool of 10. And in fact, any different arrangement of these 4 objects will result in effectively the same selection of 4, in addition to any rearrangement of these 6 objects resulting in the same selection of 4. So now, if we take our initial 10 factorial different orders to put the objects in, we know already that because of the non-selection ordering not mattering, we can divide out 6 factorial, but also the order of the selection itself also doesn't matter. So if, again, we were to list out all the 10 factorial different orders and mark off all the ones that are redundant with this one, we would find that there are 4 factorial different orderings that are redundant because of this part, and 6 factorial because of this part. So we have to divide out both. But this is indeed the correct answer. There are 10 factorial divided by 6 factorial times 4 factorial ways to select 4 objects from a pool of 10. And if we want to generalize this a little bit, if you have n objects and you want to know how many combinations of r can I pull out of them, then that will be simply n factorial divided by n minus r factorial times r factorial. So this is where it comes from. Yeah, it might seem a little weird that, the formula isn't like more mathematically tied to the concept. It's just like a really roundabout way of counting them. Like, this is where it's derived from. This weird counting method we did to count the number of ways to do this is actually directly where the formula comes from. So that's everything you need to know about where the combination and permutation formulas come from. But before I go, there's one more thing that I want to note. So here we have a brand new selection of 8 objects. Yeah, a lot of them are similar, but this, little cheese doodle is new, I guess. And what we are interested in is how many different ways are there to select some number of them. Doesn't matter what the number is, it will still count. For example, if there's a way to select 1, we're going to add that to our list. If there's a way to select 5, we're going to add that to our list. How big is this list going to be? Well, using what we just learned, there is a very simple way to count it. All we have to do is do it systematically. Take the 8 ways there are to select 0. By the way, for the future, nCr can be written as this. And this is called a binomial coefficient usually when it's written like that. And you're about to see sort of why it's called a binomial coefficient. So we have 8 choose 0. We add the number of ways there are to choose just one object out of the pool of 8. And then we add the number of ways to select 2 objects. And so on and so forth, until we get all the way up to the number of ways there are to choose 8 objects from the pool of 8, which naturally we know is just 1. You just select all of them. By the way, before you have an aneurysm, 0 factorial is just 1. So if you take 8 choose 0, you get 8 factorial divided by 8 factorial times 1. And the 8 factorials would cancel out, so you just get 1. And that makes sense. There's only one way to choose 0 objects. It's to just not choose any of them. So yes, hopefully that resolves any internal conflicts you're having about this term. But there's another way that you can count up the number of ways to do this. Let's take just this triangle and we mark it with a 1 or a 0, depending on whether we select it or not. Same thing for all the other shapes. We're going to mark all the shapes with a 1 or a 0. So there are 2 different possible markings that the triangle has, and for each of them, there are then 2 different possible markings that the square can have, 2 that the circle can have, all the way up to 2 that the cheese doodle can have. And this is just 2 to the 8th power. But what's shocking here is these were 2 different ways to count up the same quantity. So, at the end of the day, shouldn't they be equal? And it turns out, yes, they are actually equal. If you add up all of the binomial coefficients for n from 0 to n, you just get 2 to the nth power. So let me just write that down formally. God, that was the worst sigma ever, but let's just roll with it. I equals 0 to n of n choose I equals 2 to the nth power. Yeah, this is something you really wouldn't expect. Like, if you really sit down and calculate all these numbers, all these factorials flying around, and you get like crazy integers that you're not sure what they're going to end up being, but yet somehow they add up to this nice clean value just to the 8th power. It's kind of bizarre that it actually works out this way. And there are much tighter connections between the combination formula, these binomial coefficients, and the number 2. But I'm going to leave all that for another video. This just is a nice little mind-blowing fun fact to make your day a little brighter. Anyway, thank you all for watching. I've been Jake. Please leave me feedback. Let me know if this video helped you understand, if I could have explained something more clearly, or maybe I explained something too clearly, like I lingered a lot on something that didn't matter that much. Please just give me feedback. I'm going to try to improve the future videos based on this feedback. I say future videos, and I want to note that I only made this video because next week I'm going to drop a video about a very interesting problem that uses some of this stuff. And I don't want anyone to feel like they don't have enough knowledge to understand the solution. So I'm sort of starting from scratch, teaching some very basic things about combinatorics, so that video makes sense to everyone. Nobody feels left out. But yeah, anyway, do the usual commenting, and subscribing that you would do on a YouTube channel you like if you enjoyed the video. In fact, even do it if you don't enjoy the video. It helps me, all right? And please always remember to shuffle your decks. Thanks for watching. This was not as cool as it was in my head.